truly from building a pyramid in Mario to building your very own. We want to represent a 1, and let's let go of that electricity in some sense when we want to represent a 0. Pyramid that the character has to ascend. We'll recreate a portion of this game, albeit using text. Now, we wanted to evoke memories at least, or some imagery of the campus itself, particularly for the many of plus 10 times 2 plus 1 times 3, which of course is just 100 plus 20 plus 3, or the mathematical value we all know as 123. So a bit of a circular argument, but just to remind us how we got from 123 to 123. Well, it turns out that in the world of computers, the system they use is exactly fundamentally the same. The only difference is that computers only have access to 0s and 1s, not 0s through 9s. So if we consider now, in the abstract, just 3 possible digits represented here, let's consider for a moment why those columns or places were 1, 10, and 100, and so forth. Well, why was that the case? Well, there was a pattern, in fact, and it just has to do with exponents or powers. So the rightmost column, technically, if we really get into the weeds, is 10 to the 0th power, which, if you recall, just means 1. 10 to the 1st power, which is just 10. And 10 to the 2nd power, or 10 squared, is 100. But what's interesting about representing it in this way is that it jumps out that 10 is involved. There's 10 digits, 0 through 9. So the columns are using this base of 10. So you can perhaps now get even ahead of me here by considering, well, if in the binary system that computers use, you only have 2 digits, 0s and 1s, odds are the only thing that's going to change is the meaning of these columns. Now we have the 1's place still, because 2 to the 0 is 1, but then we have 2 to the 1st, 2 to the 2nd, and so forth. And of course, if we just do out that math, in the world of binary that computers use, we have the 1's place, 2's place, 4's place, and so forth. And now we're good to go. Even though we have to now think in a different base system, now we can start counting more properly. And now we can move away from the metaphor of light bulbs and consider that if all of those light bulbs are off, we're again just going to start thinking of those things as zeros. So that would be a pattern of symbols or digits that's 0, 0, 0 in binary. But in our human world, the mental math you would probably do now instantaneously after today would be, well, that's obviously 4 times 0 plus 2 times 0 plus 1 times 0, or of course 0 in decimal. But how does a computer represent the number 1, for instance? Well, it's just going to change that rightmost bit from a 0 to a 1, or more metaphorically, it's going to turn that switch on and illuminate that rightmost light bulb, just like I did earlier. How do I represent 2? It's going to be 0, 1, 0 in binary. How do I represent 3? This is where we're about to differ. Now I'm putting on 2 of those switches because I need something in the 2's place and the 1's place to give me mathematically 3. Next, if we go ahead and choose count up to 4, that's going to be 1, 0, 0. If I want to count up to 5, that's going to be 1, 0, 1. 6 is going to be 1, 1, 0. And finally, the number 7 is going to be 1, 1, 1. So it would seem that using 3 bits, each of which can be a 0 or 1, yes, you can permute them in 8 different ways. 2 possibilities for the first, times 2 for the second, times 2 for the third gives us 8. But as per this math and the intuition of starting counting from 0, we can only count up as high as 7 in total. Well, let's go ahead and actually take this out for a spin. When we don't have just, say, let's say, 1 light bulb or 3 light bulbs, we have actually the fortune of having like a whole stage worth of light bulbs. 64 light bulbs adorn the stage here. And you know what, Sumner, could we go ahead and put up a random number on the screen here? All right, so if you can see these light bulbs from your perspective, we have 8 light bulbs plus another bunch of them off, and all the others are off. So let's go ahead and ask a question then. If these light bulbs now represent not just 1 light bulb or 2 or 3, but several more, in this case at least 6 light bulbs, what value do we actually get? Well, let me go ahead and put a question on the screen here, which should pop up on yours in just a moment. And you should see now on your end this same question put in binary terms. What number in decimal does binary number 110010 represent? What decimal number does binary number 110010 represent from left to right? So here we have an overwhelming response. 50 is indeed the correct answer. Now, why is that? Well, if I go over to the physical light bulbs here, let's just consider for a moment what the pattern actually is. This here is the 1's place, the 2's place, 4, 8, 16, 32. And we could keep going, but it's not going to matter because they're all off. So we have 32 plus 16 plus 2, which indeed gives us the number you and I know in decimal as 50. And just imagine how high we could count with all of the other light bulbs as well. All right, so we started with the story with electricity. We then moved on to numbers and representing things either in decimal or in binary. But we've kind of painted ourselves into a corner, because if we only have at our disposal switches, or the metaphorical light bulbs, which we can think of as 0s and 1s, it would seem that the only things computers can do is compute. That is, behave as calculators. And in fact, early on, that's exactly what computers were designed to do, was really facilitate mathematical calculations that were otherwise quite tedious or impossible for humans. But of course, what you and I are using right now, what we use every day on our phones and our laptops and desktops, is much more sophisticated. So let's consider, how could a computer represent not just numbers, but letters of the alphabet? Brian, could we call on someone for this one? If you'd like to raise your virtual hand, how could a computer go about representing letters of an alphabet like English if, again, all we have at our disposal is switches?
We can assign the numbers that we're getting from binary to specific letters in the alphabet.
Yeah, we can assign the specific numbers in binary to letters of the alphabet. That's pretty much our only option, it would seem. If we only have the ability to permute these switches or light bulbs or bits, well, we just all have to agree how to represent letters in the same way. Now, maybe the simplest way for us to do this would be, you know what? Let's just all agree that a capital A is going to be the number 1. So you turn on one light bulb, or represent the binary number 1. Well, how about for B, we could use the number 2. For C, we could use the number, the number 3. D could be 4, and so forth. We all just have to agree to number the letters in that way. But it turns out humans did exactly that, but a little bit differently years ago. They decided, for reasons that we won't get into just now, that actually the capital letter A is actually going to be represented by the decimal number you and I know as 65. Now, in bitwise form, that's going to look like this. So this is the pattern of bits that a computer would use to represent the decimal number we now know as 65. And now what the computer is going to do is just be mindful of what type of program you're using. So yes, if you're using a calculator, or maybe using something like Excel to crunch numbers, well, in that context, when running software like a calculator or a spreadsheet program doing numerical analysis, the program is going to see inside of the computer's hardware the pattern of switches that represents the decimal number 65. And because it's in the context of a calculator or spreadsheet, what you, the human, might see on the screen is literally the decimal number 65. But if you and I are using text messaging or email or any number of social media apps where we're communicating not numerically, but in letters, say English letters, in that context, your program